Greetings, and welcome to this video example on kinetic friction. So here's the situation we're presented with. An 85 Newton weight box of oranges is being pushed across a horizontal floor. As it moves, it is slowing at a constant rate of 0.9 meters per second each second. The push force has a horizontal component of 20 newtons and a vertical component of 25 newtons downward. So let's go ahead and sketch this out after we look at step 1, what is the goal of the problem? And the goal of the problem is to calculate the coefficient of kinetic friction between the box and the floor. So let's go ahead and write that up top here. Our ultimate goal is to find u sub k. Let's sketch our situation. We have the box. We know that it weighs 85 newtons. That's the weight. We know that it's being pushed in such a way that there is both a horizontal and downward component. So the force of the push looks kind of like this. We know that it is moving, however, it's slowing down, which means that the acceleration must be in the opposite direction of its velocity. And we know that that acceleration is 0.9 meters per second every second. We can also write that as simply 0.9 meters per second squared. We're also told that there is friction occurring, kinetic friction, since the object is in motion. That's our general sketch. Let's go ahead now and draw the official force diagram for this box. Just do a little dot here to represent the box. We have the downward force of gravity equal to 85 newtons. We know that the box is resting on the floor as it slides along, so the floor must provide some amount of normal force. We know that the pushing force is forward and downward, F push, and we know that friction is opposing the motion. So it must be pointing to the left in this particular case. We're also told that the two components of the pushing force are as follows. We have a 20 Newton force horizontal, and we have a 25 Newton force vertically downward. That's nice that they give us these, because that means we don't have to just start with the pushing force and break it down into its components. It's already been done for us in this particular situation. So, now let's look at the net force in each dimension. We know that the vertical net force must be 0 because the box is not accelerating upwards or downwards. So that 0 net force is also equal to, in this situation, if we define up as positive, the normal force minus force of gravity and minus the force push y component. If we plug in numbers, then that means that we have the normal force minus 85 newtons minus 25 newtons. Since we know that all that must come to 0, we only have one unknown here, the normal force. So we can go ahead and solve for that. You should be suspicious that we might need to figure out the normal force, because keep in mind that our equation for the kinetic friction is equal to mu sub k times the normal force. So let's go ahead and solve for that normal force now, since we can. That's equal, the strength of the normal force is going to be equal to 85 newtons plus 25 newtons, or simply 110. So let's go ahead and put that down there. Okay. Now, let's have a look at the net force in the x direction. There is acceleration in the x direction going on. So now we can think about Newton's second law. Newton's second law says that the total net force must be equal to the mass of the box times its acceleration in x. In other words, it must be equal to the mass of the box times 0.9, and again, if we take the left as negative, it's negative here, meters per second squared. So, what is the mass of the box? Well, we can actually find that out because we know the weight. Fg equals mass times the acceleration due to gravity. So mass will be equal to 85 newtons, the total weight, divided by 9.8 meters per second squared. That means that the mass of the box must be 8.673 kilograms. So we plug that in here for m, and we get an answer of, let's see here, 7.81 newtons. So that is the net force that is occurring on the box in the horizontal direction. What else is the net force in the horizontal direction equal to? Well, it's just equal to all the forces that add up along that direction. So that would be, again, assuming that the left sign is negative, and actually because of that, I should remind myself there's a negative there, so we'll put the negative there. Negative 7.81 is equal to the friction force, which is also negative. And then we're going to add the horizontal component of the pushing force, which we're given to be as 20 newtons. So we can plug in 20 newtons here. So given this relationship here, you see that we can solve for the friction. Friction force is going to have a strength that's equal to 20 newtons plus 7.81, which is simply 27.81 newtons. This is the force of kinetic friction in this particular situation. And if that's the strength of the friction force, then we can use the equation we wrote up here to solve for mu sub k, because we already calculated the normal force earlier on in the problem. So that means that mu sub k is equal to the strength of the friction force. To just emphasize that, I'll put the absolute value signs here. Strength of the friction force divided by strength of the normal force. That gives us 27.81 newtons divided by 110 newtons, which gives us a final answer of 0.25. Since the coefficient here is a ratio of two forces, the units cancel out. So this will be one of the very rare cases in the class where your final answer actually will not have any units. It is a ratio and thus just a number. This concludes this video example on kinetic friction. Thank you for your attention.